Welcome back. We're going to finish up in this lecture the algorithm for finding a largest cardinality common independent set. So again, our problem is given matroids M1 and M2 on common ground set, we want to find an element of the intersection, a common independent set, maximizing its cardinality. In the previous lecture, we took two important steps to doing this. First, we defined a directed graph as follows. We defined dm1, m2 of an independent set I to be the graph that has on the left edges in I, on the right has all of the other edges, all of the other nodes, elements of the ground set, and it has an arc set A of I where an edge between an element y on the left and an element z on the right always means that I minus y plus z is an independent set, and then the directionality of it tells us if it's an independent set in Matroid 1 or Matroid 2. So in this case, let me put this z1 here. This directionality from left to right tells us that this is an independent set in I1, in Matroid 1. And if I had another edge, again, it means that if I subtract y and add z2, it's an independent set. But because of the directionality, this tells us that it is in I2. We also defined x1 to be all the nodes, to be all of the nodes on the right, such that I plus z is an independent set, and similarly x2 to be all the nodes on the right, such that I plus z is an independent set in Matroid 2. And in the last lecture, we looked at case 1, which says if there exists an x1 to x2 path in A of I, then if P is the shortest such path, then I dash, which is equal to I symmetric difference with the vertices in this path, shortest path P, is an element of the intersection and an element of and an independent, common independent set of cardinality 1 greater. So now we're going to look at this other setting, which is the situation where there is no such path. So case 2 is that this graph, dm1 m2 of I, has no x1, x2 path. And in this case, we show that I is optimal. I is a max size common independent set. So here's how the proof is going to go in pictures. It's based on a particular existence of a particular set, and I'll leave this as an exercise. If no x1 to x2 path exists, then there must exist a set U with no intersection with x1, fully containing x2, and so that no arc of A of I enters the set U. No arc enters U. So again, looking at our picture, here is I. Here is E minus I, and remember that we write it as here's x1. Here are some nodes that are neither in x1 nor x2, and here are nodes in x2, and that we have various edges. And what we're saying here is that we have some set U, and perhaps it looks like this. And note that, again, it has no intersection with x1. It fully contains x2. And inside here, I could have any collection of edges. I could have edges outside of going outside of the set. But I have no edges going into the set. So I'll leave this for you as an exercise. Essentially, it's a cut with 0 edges, which is saying that we can't have, which is equivalent to saying that there is no path from x1 to x2. Okay, let's continue with this proof and use this property. And the proof essentially follows from the following claim: that Rm1, the rank in Matroid 1 of U, plus the rank in Matroid 2 of the complement of U, is less than I. And once we prove this claim, the proof follows immediately from the Matroid intersection theorem, which we proved in our first lectures on Matroid intersection. So we're going to prove this claim in 2 parts. Actually, we're just going to prove the first part. The second part it follows by a symmetric argument. So in the first part, we're going to show that Rm1 of U is less than the cardinality of I intersect with U. And then in the second part, we would show that Rm2 of E minus U is less than the cardinality of that set, and therefore this will essentially follow. So in order to prove this inequality holds, suppose it doesn't. So if it doesn't, in other words, if the rank of U is strictly bigger than the cardinality of I and U, then there exists some x that is in U but not in I, with I intersect U plus x still in I1. But on the other hand, we know that I plus x can't be in I1. So how do we know that? Because x is in U, we know that x1 has no intersection with U, and therefore any element of U has to be in the span of I. So in other words, I plus x is not an element of I1. Otherwise, we would have x in x1 contradicting that U intersect x1 is empty. Let me rewrite this a little bit more clearly here. I see that it's okay. So we know that I plus x cannot be in I1. So what does that mean? As soon as we have a dependent set, we know that there has to be a circuit. So I plus x not in I1 implies that there exists a circuit that's a subset of I plus x. And in particular, x has to be in that circuit. So let me give it a name. There exists a circuit C with x in C. We know that there's no circuit in I because I is an independent set. And moreover, again, we know that C intersect with whatever is in I minus U can't be the empty set, since again, we know that I intersect U plus X is independent, is in I1. So this tells us that there exists a Y that's in the complement of U in I, that it's in I but not in U, with I minus Y plus X, which is an I1. And you can think where the contradiction is. You see that? This is exactly saying, this statement is exactly saying that the arc YX is the arc YX is in A of I. But that can't be, because that means that there exists an arc that enters U. And this is our contradiction. The second part of the proof we won't do in detail, but I'll just write the statement. It says that the rank of the complement of U, or the same set U, is bounded above by the cardinality of I minus U. And I'll just leave this as an exercise and say that it follows similarly. Now this proves the claim, and then the proof of optimality follows from the Matroid intersection theorem. This proves the claim, and optimality follows from the Matroid intersection theorem. So that concludes the proof and of correctness of the algorithm. It's easy to see that this algorithm proceeds in polynomial time. And at each stage, it either augments I by 1, or it asserts that I is a maximum size common independent set. After this, it's time for us to tackle the polytope for Matroid intersection, as well as an algorithm for the weighted Matroid intersection problem. And we're going to pick that up in the subsequent lectures.